Okay, welcome to the next lecture for ES 300. Today we're going to talk about natural gas. So the three quasi-final exam questions for today are: what are the benefits of natural gas as a fossil fuel in power plants compared to coal? What are the implications of low natural gas prices on the electric power industry? And what are the climate change implications of low natural gas prices? So natural gas is a hydrocarbon gas mixture consisting primarily of methane, so CH4. It's found in a couple different places, deep underground rock formations, or associated with oil reservoirs, coal beds, and also methane clathrates. So let's talk about its role as a fuel. So during most of the 19th century, natural gas was used almost exclusively as a source of light. So here's an example of some natural gas lighting. This was also featured prominently in the new Mary Poppins movie, which I've seen twice because of my children. That's pretty good, actually. So Lin-Manuel Miranda's character is a lamplighter in this movie. And it's also sort of the origin of this phrase to gaslight someone, which comes from an Ingrid Bergman movie. So the premise of this movie, I think, if I remember correctly, is that there's this guy that marries this young woman, and the guy only marries her because he wants to live in her house. So because he knows there's some sort of not buried treasure, but some sort of like hidden wealth inside the house, and he needs time to discover where it's hidden. And so, but he also needs to get rid of her. And so his plan for getting rid of her is to make her believe that she's crazy. And so the way he does this is that he'll turn on and off or dim the gaslight in the house, so that the woman thinks that she sees the lights that are going brighter and dimmer, and then she'll say, "Well, did you notice that?" And he'll say, "What are you talking about? I don't see anything." So the phrase "to gaslight someone" comes from this movie. And it just means to make someone feel like they're crazy. So once pipelines were built in the 20th century, the use of natural gas expanded to home heating and cooking, water heaters and oven ranges, manufacturing and processing plants, and most importantly for our discussion, electric power plants. There are two main types of natural gas power plants. The first type are natural gas combustion turbines. So these are sort of like jet engines. They have a pretty low thermal efficiency of between 20 and 35%. Which means that they're able to convert at most 35% of the actual energy content of the natural gas to electricity. So the energy starts out as chemical energy embedded in the natural gas. The natural gas is injected into a combustion turbine, so it's mixed with air and burned, and that energy spins a turbine. So the natural gas is then converted to thermal energy, and then as the energy is spinning the turbine, that is converting thermal energy to kinetic energy. And then the turbine is, of course, spinning a coiled conductor within a magnetic field to generate electricity. So then we're converting the kinetic energy to electric power and energy. So there's no steam involved here at all. You're just using a combustion process, a mixture of air and natural gas to fuel a combustion process, and that energy released spins a turbine. So combustion turbines, because of their really low efficiency, have very high variable cost rates, so dollar per megawatt hour cost associated with producing electricity. So their traditional position in the supply curve has been pretty high up. They're pretty expensive, right below oil diesel generators. So natural gas combustion turbines are mostly used to provide reserves, respond to grid emergencies, and provide peaking power. So they're very expensive, but also very fast. So we would typically see them acting as peaking resources, so only producing electricity when demand is really high. So the other type of natural gas power plant are natural gas combined cycle. And so what's interesting about these types of power plants is that they combine two different electric power generation systems. The first is a combustion turbine, just like what we just saw. And so the mixture of air and natural gas is used to fuel a combustion process which spins a turbine and generates electricity. So remember, we talked about how only 35% of the actual embedded energy in the natural gas can be recovered through a combustion turbine. The rest, the 65% of electricity or energy that's not captured, is typically lost as heat. So what natural gas combined cycle power plants do is they take that excess heat and they apply it to water to create steam. And so the excess heat from the combustion turbine is used to convert water to steam, and then that steam is part of a steam generator that's on site as well. And so that's sort of what this looks like. The top part is the combustion chamber. So you're mixing natural gas and air and fueling a combustion process. That spins a turbine and generates electricity. And then that exhaust heat is passed through some sort of coil that has water in it. And that water is heated up into steam and then passed through a steam turbine, just like what we saw for a coal-fired power plant. So you have two different sources of electricity here, and what that ends up meaning is that these power plants are able to capture more of the embedded energy in natural gas and convert that to electricity. So these plants are very efficient. About 60% thermal efficiency, which is twice as high as regular coal and combustion turbine natural gas plants. So because of their greater efficiency, their costs are much lower than combustion turbine natural gas plants. And so these traditionally in the supply curve have been pretty low, just above coal. Now, of course, the position in the supply curve also depends on the price of natural gas, and we'll talk about that in a few minutes. But these power plants have been capable of providing base load as well as peaking power. So apart from that, natural gas combined cycle plants pose relative to both coal and combustion turbines pretty significant environmental benefits. So about half the CO2 emissions of a coal plant, no thermal pollution. That's because they don't have, they use different cooling systems that rely significantly less on cooling water. So they discharge less heated water back into rivers and lakes. No emission of mercury or almost no emission of NOx and SOx. And that's just because of the lower presence of these chemicals in natural gas. And then no solid waste removal. So that has led to many people describing natural gas power plants, in particular combined cycle units, to describe them as a blue bridge to a green future. And that's sort of a reference to the blue color of the flames produced. And so they're also more flexible, which means they have lower start costs, higher ramp rates, so they can turn it on and off more quickly. And once they are on, they can ramp up and down more quickly, especially compared to coal plants. And we already know that one of the issues with reducing our reliance on coal plants entirely is that if we want to replace those with renewables, we have to have some other type of dispatchable generation to complement the renewables. So the times when wind and solar are not available, we need something else to step in and replace that. And natural gas power plants are sort of uniquely positioned to help integrate variable renewable energy. So recently, most new power capacity in the United States has been a combination of combined cycle natural gas power plants and renewables. So where is natural gas located globally? So this is a much different list than what we saw for coal. Remember, we talked about coal. One of the reasons coal is so cheap and used widely in the electric power industry is because a lot of the countries, number one, it's abundant, and a lot of the countries that own most of the reserves are geopolitically stable. And so we could not really say that about this list. We're talking about Russia, Iran, US, Saudi Arabia, the UAE, Venezuela has had all sorts of problems. And part of this is because natural gas is often found and is co-located with oil reserves. And so these countries are also really, really big oil producers. Within the United States, natural gas reserves are located mostly in Appalachia, so West Virginia and Pennsylvania. That's the Marcellus Shale, the Mountain West, Wyoming, Colorado, and then Texas, the Gulf region, so Texas, Oklahoma, and Louisiana. So fossil fuel reserves, that map that I just showed, refers to resources that are known to exist, but would also be economically viable to extract using current technology. So that doesn't mean that there is not as there that that's the amount of natural gas that's actually under the ground. That's the amount of natural gas that's estimated to be under the ground that engineers and economists think that using current technology, it would be reasonable to expect that people would extract and use and sell. So, given that definition, what we see over the last several years is that natural gas reserves in the United States have increased dramatically, basically since the early 2000s. And so a question is why did reserves go up? Does that mean that natural gas is increasing in abundance under the ground? It's actually not that, right? It's because if we stick to this strict definition of reserves as available resources that could be extracted and sold in an economically viable way using current technology, well, the part of that has changed is current technology. And so reserves in the United States have increased dramatically because of the invention of horizontal hydraulic fracturing, which is shown here. And so this is this fairly novel way of extracting natural gas out of the ground by drilling a hole down into the ground into rock that is sort of imbued with natural gas, and then drilling horizontally. And so, natural gas deposits, rock that contains natural gas, is sedimentary, the same way coal is. And so the same way that mountaintop removal and surface mining was discovered to be a more economically efficient way of extracting coal, horizontal hydraulic fracturing, because of the horizontal nature of sedimentary rock and the rock that contains natural gas in some cases, this has become a much more cost-efficient way of extracting natural gas, and so reserves increase. So the natural gas industry has different sort of hierarchies or levels, similar to the way that we look at the electric power industry. So there's production and processing. So this is drilling and well completion, producing wells, gathering the natural gas, and processing the natural gas, so removing any sorts of impurities. And then we have transmission and storage. So natural gas is a pipeline fuel. So we have to have pipelines in place from where it's produced and processed and then delivered to places of storage, and then ultimately delivered to end uses. So that would be the third part, the distribution part, where you're delivering natural gas to industrial users, power plants, residential customers, etc. So natural gas transport is, at least domestically in the United States, entirely transported by pipeline. Increasingly, natural gas is at least as it involves the United States, is also transported via tanker in a liquid form. So you pressurize natural gas to extreme levels, it turns into a liquid, and then it can be more easily shipped. This is pretty new. For a long time, because of how important natural gas was for not only electric power generation, but also heating, the United States had a longstanding policy of not exporting any natural gas, and that has changed in recent years because of increased supply from fracking, horizontal hydraulic fracturing. And so now we are beginning to ship liquid natural gas to other places in the country. So this map gives you a sense for the order, the scale of natural gas, international natural gas trade. The blue lines represent liquid natural gas, and red lines represent pipelines. So within the United States, this is a map. It's a bit older, but it's a map of natural gas pipelines. So clearly a lot of natural gas pipelines, where we see a lot of natural gas production in the Gulf Coast and the Marcellus Shale. And then natural gases lines are sort of snaking everywhere across the rest of the United States to deliver natural gas from these hubs to storage areas, and then ultimately to residential, industrial, and commercial applications. So this is a picture of a liquid natural gas ship. So the big domes are where the natural gas is held. And again, it's pressurized to a point where these are all liquid. So I don't actually want to see one of these blow up. It just looks like it's something that would make a very big bang if it did. So natural gas storage. So after natural gas is produced, It's often treated or processed to remove any sort of impurities. It's often stored. Now, storage of natural gas is a lot trickier than storing coal. Coal you can just sort of dump outside of a power plant that you want to where you want to use it. Storing natural gas is much more complicated. So natural gas storage is principally used to meet load variations or fluctuating demands for natural gas. So the typical rule of thumb is that we store natural gas during periods of the year when demand is low, and that could be spring or the fall. And we withdraw from natural gas storage during periods of peak demand, which would be the winter or the summer. So the most important types of gas storage is actually underground reservoirs. There are three main types. Depleted gas reservoirs, so that means essentially places that we originally removed natural gas from the subsurface. We actually can pump natural gas back in and store it there and remove it when we want to. Also saline aquifers and salt caverns. The most of the natural gas storage in the U.S. is from depleted natural gas or oil fields that are close to consumption centers. And so there are lots of reasons why we take advantage of these depleted fields, because there's already existing infrastructure there. There's wells, gathering systems, processing centers, and pipeline connections. So here's a map of existing natural gas storage in the United States. So again, mostly concentrated around the areas where we're producing natural gas. In the Gulf Coast region, in the Marcellus Shale, there's some in the West Coast in California, and in the Midwest as well. And so you can look at the different types of storage by the shape and the color. So in the 1980s, a movement towards deregulation of the natural gas industry began. And so now today we have, similar to many places in the U.S., vertical disintegration of the natural gas industry. So there are, in theory, different companies that are producing the natural gas, refining it, transporting it, storing it, and then distributing it on a retail level to end-use customers. So we can sort of divide this this flow of natural gas from production and processing to natural gas transmission and storage and distribution into three main parts here. And so what that means is that there are wholesale markets for natural gas and retail markets for natural gas in a very similar way that wholesale electricity markets work, where they're sort of existing to allow for the bulk buying and selling of natural gas between producers and buyers. The buyers would be distribution utilities. And then the distribution utilities can distribute that to end-use customers, and they sell it at a retail rate. Okay, so let's talk about natural gas prices, because this is where things get to be really interesting for the electric power industry. So wholesale natural gas prices are driven by fluctuations in supply and demand. So we have a pretty liquid market for natural gas where market forces apply. So we're thinking again in terms of wholesale prices for natural gas being driven by the intersection of supply and demand. So the point on the y-axis that's associated with the intersection of supply and demand here would give us a market clearing price. So what affects the supply of natural gas? So there's a couple different factors. The first would be the variation in the amount of natural gas that's being produced. Because we don't have an ability to store vast quantities of natural gas the same way we have an ability to store vast quantities of coal, the natural gas that we want to use is more directly impacted by recent production levels. And so that could mean production at wells or activities at refineries. Also included in this is the amount of natural gas in storage. So the way natural gas is produced and delivered to end-use customers, that natural gas has to either be immediately produced and processed, so taken out of a well, processed and put into a transportation network, or it has to be taken out of underground storage. And so there are events that can impact the production of natural gas. A really important one would be Gulf occurring hurricanes, given the fact that a lot of natural gas production and processing happens in the Gulf region. Gulf occurring hurricanes can disrupt a lot of those activities and drive supply down. So what we see throughout history when you have Gulf occurring hurricanes that disrupt natural gas production activities, the supply curve shifts inward to the left, and demand doesn't change. So demand, at least in the short term, is pretty inelastic, and so that you can get a really big spike in the price of natural gas. Other things that could change the supply more over the long term would be new technologies that are able to produce natural gas more efficiently or more cost effectively. So an example would be horizontal hydraulic fracturing. If we look and see what fracking has done to, in general, natural gas supply and markets, the system supply curve shifts out to the right, meaning that we can get the same amount of natural gas for a lower price. And that causes the market price to drop. So what do you think impacts demand for natural gas? So two demand side factors that could affect prices would be the level of economic growth and also weather, especially heating and cooling demands. A really prominent example of this is when the Northeast or the Midwest is impacted by polar vortex weather events, which drives a lot of very cold Arctic air down into the United States. Heating demands in the Northeast increase significantly, and so demand can shift out to the right while supply is pretty fixed. If we don't have with short-term events like this, weather, meteorological events where you have like a 2-week cold snap, there's not a great ability for the natural gas market to increase production over that time period. So supply might be more or less fixed and inelastic, while demand increases, and then again, you can get spikes in the price of natural gas. So this is what natural gas prices look like from the early 2000s to mostly present day. And so a lot of volatility. I mean, if you remember, and we'll see another figure like this in a few minutes, but if you think about what coal prices looked like compared to natural gas prices, coal is abundant, it's easily stored, it's cheap, and prices are flat and low. Natural gas prices have been extremely volatile at different points over the last 20 years. And each one of these, changes in the price of natural gas, we can, in some cases, tie to significant events. So the first red dot here is the California energy crisis. So we talked about that a little bit. You read about it for one of your homework assignments. Deeply involved in the California energy crisis was market manipulation that was being carried out by a company called Enron that was purposefully withholding supplies of natural gas. At the same time, we had a drought in California, a heat wave, so electricity demand was increasing. So you had increased demand for natural gas and reduced supply, and that drove prices really, really high, which is exactly what the guys at Enron were trying to do because they were trying to make money. In December of 2005, August of 2005, we had another significant event that disrupted natural gas production, which was Hurricane Katrina, and I just showed a map of that. So that resulted in an all-time high in the price of natural gas. And then let's look down here. In more recent years, prices have been way less volatile and much, much lower. And so this is associated with decreased demand, overall, reduced economic activity, and increased supply from frack. So let's talk about fracking. So fracking refers to the horizontal hydraulic fracturing. So the horizontal part is the part that's most important, probably, in terms of leading to cost-effective extraction of natural gas, and it's the innovative part. We've been hydraulic fracturing for a long time. And so the reason this is important is because sedimentary beds that are geological features that contain natural gas are usually nearly horizontal. So by drilling horizontal wells, we have a much larger contact area with the target formation. And so some of this drilling can go out tens of thousands of feet. So this is the Barnett Shale. This is just a sort of a schematic of what this looks like again. The Barnett Shale in Texas, there's drilling up to 5,000 feet. And in the Bakken Shale Formation in North Dakota, drilling is up to 10,000 feet, which is ridiculous. That's an extremely long distance to be drilling out horizontally. So this is a schematic of the Barnett Shale, just in terms of showing you the history of natural gas production from the Barnett Shale. So basically nothing in 2000, and now producing billions of cubic feet per day. It's amazing. And all these red dots around the Dallas-Fort Worth area are are different natural gas wells. The other really big horizontal hydraulic fracturing center is the Bakken. And so this is in North Dakota. This is where a lot of the shale oil is coming from as well. So again, early 2000s, nothing. And now producing almost, on the order of a billion cubic feet per day. And then there's the Marcellus Shale. And so this is throughout Appalachia, big part of Pennsylvania, West Virginia. Again, early 2000s, not much natural gas coming from here. And now we're on the order of 15, 16 billion cubic feet of natural gas per day. So what this has resulted in is increased natural gas reserves in the United States. It does not mean that there's more natural gas under the ground than there used to be. It means that there is more natural gas under the ground that we can, with current technology, extract in an economically viable way. And so you can see that now unconventional natural gas reserves, which would include shale, are almost half of total U.S. Proven reserves. So fracking is controversial, and that's because of air emissions. So, all natural gas production and processing involves fugitive emissions of methane, which is a very potent greenhouse gas into the atmosphere. And I think the concern is that an increased reliance on fracking may result in increased fugitive methane emissions. High water consumption, although the life cycle use of water for coal-fired power plants is typically, especially older coal-fired power plants, is typically higher than natural gas power plants, but it's still a concern. Groundwater contamination at the well site, surface water contamination of the spill, and I think the idea here is that the fluids that they inject into the rock formations to help with the fracturing process contain chemicals that could be harmful for people. Land use, risk of earthquakes, tectonic activity, noise pollution, and health effects on humans. So many states have decided to ban this practice, including New York. However, we have now experienced about 10 plus years in a row of really low natural gas prices as a result of fracking. And this has had a transformational impact on the electric power industry that's worth discussing. So one of the first things it's done is been responsible for what we call the coal to natural gas switch. So the first thing you have to know is that the price difference between coal and natural gas has narrowed significantly. So we can compare the price of natural gas and coal in a common term, which is the dollars per million British thermal units, or a million BTUs. So this is comparing the dollars per unit energy embedded in coal with the dollars per unit energy embedded in natural gas. And so after decades of natural gas being more expensive than coal and more volatile than coal, in recent years, natural gas on a per unit energy basis has basically been equivalent to the cost of coal. And so at the same time, you have environmental regulations that have been hammering the coal-fired power plants and as a byproduct of that, the coal industry. So you have the Clean Power Plan, which is not currently active, but could be, I think, reactivated, at sort of a moment's notice if we had, a different president. Mercury and air toxics, the part of the Clean Water Act that targeted cooling water systems, and then also coal ash removal and storage. So what this means is that if you add in the cost of new environmental regulations, electricity from coal is now more expensive than electricity from natural gas. And so existing coal-fired power plants are being in deregulated markets where they're having to compete on the basis of cost in order to sell electricity, are now being outcompeted by natural gas power plants, which means the coal power plants are not able to sell as much electricity. Another important effect is that natural gas prices have reduced wholesale electricity prices. So remember that the marginal cost of electricity from different power plants, especially thermal power plants, is directly related to the fuel cost. So the marginal cost of electricity from a coal-fired power plant goes up if the cost of coal goes up. It goes down if the cost of coal goes down. And that was the original inspiration here for showing a range of different marginal cost values associated with natural gas power plants. And that's because over the last 20 years, the price of natural gas has been so volatile that sometimes the cost of electricity from a natural gas plant is really cheap, and sometimes it's been really expensive. Now today, because of fracking, because of increased supply from natural gas, the cost of electricity from natural gas plants is cheap. And so what that means when we put together a system supply curve, remember how we do that when we list order or power plants in order of increasing marginal cost, and we stack them in terms and account for the cumulative quantity that could be supplied, and then plot those ordered pairs. We get a system supply curve. So when the price of natural gas is low, the marginal cost of electricity from natural gas plants gets lower. And so the part of this system supply curve that's associated with those natural gas power plants drops down. And so when the price of natural gas is lower, we get a system supply curve that looks like this one shown here in green, as opposed to the one shown in red. And so if we're talking about the wholesale market for electricity, which we know is driven by interaction between supply and demand, if the system supply curve if the system supply curve changes, that means that the price of electricity is going to change. So let's take a look how. So let's assume that demand for some hour is on the order of 17,000 megawatt hours, and we can look at the difference, the vertical difference between the intersection of demand and supply in a case where natural gas prices were pretty high, which would be the red curve, and a case where natural gas prices are lower due to fracking, which is this green case. And so the vertical difference between these two green lines would be the difference in the market price of electricity just due to a reduced price of natural gas. So all this is to say that wholesale electricity prices often track natural gas prices, and that's because natural gas power plants are often the market clearing unit. In other words, they're often the most expensive power plant that's used to meet electricity demand, and that's generally how we set wholesale prices in competitive markets. Therefore, wholesale electricity prices and natural gas prices tend to be pretty strongly correlated. So back to coal plants. For existing coal-fired power plants that stay online, they have higher fixed costs because they have to adhere to these new regulations, which means they have to build a bunch of new stuff to get rid of NOx and SOx from their smokestacks, to install a different type of cooling system, to get rid of emissions of mercury and other air toxics. So they have to spend a lot more money, borrow a lot more money to build stuff, so their fixed costs go up. And they're being outcompeted in wholesale markets by lower priced natural gas power plants. So they have lower revenues, and the electricity that they do sell is not worth as much because natural gas power plants are pushing down the market clearing price. All of this has led to a massive amount of coal-fired power plant capacity being retired in recent years. And this is one that we talked about last time, and we asked ourselves the question, well, why aren't more coal-fired power plants retired? And part of that has to do with the market not being able to rely mostly on renewables. Part of it might be because utilities are afraid that the price of natural gas might go up again and behave in a more volatile way, similar to the way it behaved over the last 20 years. And the other part of it is because of the fear of stranded costs. So you don't want to retire a coal-fired power plant if you're not done paying off its mortgage. So a lot of the coal-fired power plants that are retiring are being replaced by a combination of natural gas and renewables. So a lot of these older plants that were built in the 70s and 80s are now being replaced with gas and renewables. And this has led to a decline in emissions, right? So 28% relative to 2005. And that's great news. But we still have a lot of work to do. We need to get this number down from 1750 to zero. Because remember, emissions from the electric power industry are only 25% of global greenhouse gas emissions. So, and it's the easiest one to fix. So we really have to get it to zero. So, there are some issues with the potential for low natural gas prices, even though it has resulted in a decline in emissions or helped contribute to a decline in emissions over the last several years because it's been responsible for the coal to natural gas switch. Low natural gas prices do not necessarily mean we are headed to lower, significantly lower carbon emissions. And that's because low natural gas prices, which mean low wholesale electricity prices, also impact some of the technologies that we do want to promote, which would be wind, solar, and even nuclear power. So how do low electricity prices impact these other sources of generation? So it impacts their net present value. So if we're thinking about discounting profits out into the future, for example, for a wind or a solar farm, it can cause problems because it doesn't mean the costs for these projects go up. You know, the cost of a wind farm, the cost of a solar farm is the same whether the price of natural gas is high or low. What it does impact are their revenues. So if you're a wind farm or a solar farm and you're just selling electricity whenever the wind's blowing or the sun's shining, the amount that you might get for that electricity could be tied to the wholesale price of electricity. And if prices are low because natural gas prices are low, that means the same project, the cost the same, is now making less money. And so it makes it more difficult for these projects to pay their mortgage on time. So unfortunately, the same force that has helped us close a lot of coal plants, which is low natural gas prices, fracking, causing low natural gas prices, causing lower electricity prices, is also keeping some renewable energy and especially nuclear power projects from being developed. So that's it for today. We're going to talk next time about nuclear power plants. So see you there.